Okay, I'll get started. Wanted to begin with an announcement. It's an announcement related to Test 1. So Test 1 is next week, is next Thursday. Test 1 is in this classroom next Thursday. Test 1 is one hour in length in this classroom. So the test will have 3 problems, 3 numerical calculational problems on the test, and then some true-false questions are on the test. So the true-false questions are in the spirit of the lecture quizzes that we do. They're sort of ideas, concepts. The problems on the test are in the spirit of the work you do in your tutorials, in recitation, and the work you do in your homework. So the idea is that the lecture quizzes and the tutorials in recitation and the homework that you give in on Mondays, they're all preparation for the content of the test. There's a practice test in our Canvas modules directory. I think it's called the practice test modules. There's also the formula sheet that you get in that directory. I believe I've got a practice test without the solutions written on it and another one with the solutions written on it. I would recommend starting with the one without the solutions and practice as if it was a real test. The material on the test is all the material that we will have covered by the test day. So it's all the material we covered up to now, plus today's lecture, Thursday's lecture, and next Tuesday's lecture. So is this a list of material that is in the syllabus? It's all our material on electricity. So it's the sort of theoretical work we did on electricity with Coulomb's law and the electrical force between electrical charges, and thinking of Coulomb's law in terms of electrical fields and electrical fluxes and electrical potentials to understand Coulomb's law. It's also the material that we're doing now on electrical circuits that will involve capacitors. We met them today. Resistors, we'll meet that. Batteries, we'll talk about that today and on Thursday, and so on. So that's the content. Any questions on all of that? Okay, well, if some questions come up, you can just email me. I'll give you a reminder again of the test on Thursday's class and Tuesday's class. But if not, I'll go on with the material for today. So today we're going to talk about electrical currents and electrical resistance, basically those 2 topics. And I'm going to walk my way through these 3 bullets here. So we're going to talk about electrical currents and how we visualize them sort of macroscopically or globally, and how we visualize electrical currents microscopically at a small scale. And those 2 ways of picturing electrical currents will come with a pair of equations. We'll introduce a pair of equations. I'll then talk about resistance, resistivity, and Ohm's law. These are all connected things, connected to electrical resistance of materials, substances. And then I'll talk about energy and power, joules and watts, energy and power in electrical circuits. And so we'll try and get through these 3 bullets. I should say one thing about electrical circuits that is different from some statements that we made when discussing Coulomb's law and the workings of Coulomb's law. When we discussed Coulomb's law and the workings of Coulomb's law, we talked about conductors and insulators. We said that insulators in equilibrium have no field in them, 0 electrical field, and they have a constant electrical potential over them and within them. That's a statement about conductors in equilibrium. in electrical circuits, we started meeting electrical circuits last class. We're going to talk about electrical circuits this class, the next class, and the following class. The conductors aren't in equilibrium. They're not in equilibrium. The charges are still flowing around, moving around. So the electrical fields in the conductors we're going to meet today and in the next classes, the electrical fields are not zero in the conductors because the conductors are not in equilibrium. The potentials are not constant in the conductors because the electrons are still in motion. The conductor is out of equilibrium, in non-equilibrium. Okay, so our class today is going to be based on a rather simple, straightforward circuit. It's pictured here. It's a circuit that contains components you already know. It contains a battery. It contains a resistor down here. This resistor is a light. And this was a circuit that was first put together about 200 years ago. This circuit came about from a great invention that's important to all our lives. And it was the invention of the battery that occurred 200 years ago. It was an invention due to Volta 200 years ago. And it was an invention that was based on his understanding, his discovery, his finding that chemical reactions, chemical processes can create electrical potentials, electrical potential differences. And a battery that you buy at Kroger's, or a battery that's in your phone or your laptop or your iPad, those batteries use chemical reactions, chemical processes to produce a voltage difference, a potential difference that ultimately supplies the energy, supplies the power to your iPad or laptop or phone. So that was a huge, absolutely huge invention. And it actually freed scientists working on electricity, electrical problems, from having to create, imagine this, having to create electrical charge by rubbing things every time. It freed them from that. Now they could create electrical charge, use electrical charge from batteries. So that was a massive scientific breakthrough, but also it was a massive technological breakthrough because every one of us is using batteries all the time. Okay, I got two slides to just show you the circuit as a circuit diagram and two ways we can think about the circuit as a circuit diagram. So here's that circuit, here's the battery, here's the symbol for the battery. Remember, it's a symbol with a long arm and a short arm. The long one is the positive arm because you can cut it in two and make a plus sign. The short one is the negative terminal because you can't, it's too short to cut in half and make a plus sign. Here's the resistor. This is the symbol we use for resistor downstairs here. And one way you can think about an electrical circuit is in terms of our force perspective that we were talking about in the context of electrical forces and so forth. So in that context, the battery is kind of pushing, shoving the electrons around the circuit, around the wires, through the resistor and back to the battery. So it's kind of pushing them or kicking them or whatever. In this picture of forces, the resistor is kind of well, it says it's a resistance, a drag on the motion of the electrons around the circuit. So the resistor is resisting this push from the battery, this kick from the battery. It's a drag on that kick or push from the battery. And so from the perspective of forces, there's really two forces going on in the electrical circuit here. There's a force, chemical in origin, coming from the battery, a force, a drag force, physical in origin, coming from the resistor. It's a bit like raindrops falling. Especially raindrops fall, they don't keep accelerating, actually they fall if you look at raindrops, they fall at constant velocity. They've reached a terminal velocity, a final velocity, where there's this balance between gravity pulling them down and the drag of the air that they're flowing through counteracting the gravitational pull. And the same sort of thing's happening here. There's a force from the battery pushing the electrons around the circuit, and then there's a drag force on the electrons that is resisting their flow around the circuit. So it's just like raindrops falling to the ground, but in an electrical rather than gravitational context. But in both cases, there's drag forces that are opposing the gravitational or the electric forces. Here's another way we can think of the circuit. We can think of this battery as actually a source of energy. It's chemical energy, but it's a source of energy for the circuit. It's a source of power for the circuit. Remember, power is the joules per second, the amount of energy per second, per unit time. And so the battery is a source of power and energy. The resistor is something that dissipates that energy, dissipates that power. By dissipate energy, dissipating power, we don't mean destroying energy and power. You can't destroy energy. What we mean is that energy that's owned by the electrons flowing around the circuit is just turned in, it's dissipated in, it's turned into heat, warmth of the resistor. So if you switch this circuit on, the resistor gets warmer and warmer because energy is being dissipated into it. Electrical energy has been turned to heat energy in the resistor. So the battery is supplying that energy through chemical processes. The resistor is dissipating that energy through physical processes that turn it into heat. That happens when raindrops fall too, right? The gravitational force is transferring energy to the raindrops, but the drag force, right, is dissipating that energy from the raindrops. So the raindrops never get faster or slower because of this balance between the gravitational energy that's flowing into the raindrops and the dissipation of energy from the raindrops into the air is actually getting hotter or getting warmer. The raindrops are getting hotter and warmer through that dissipation. Okay, let's talk about electrical current now. So firstly, electrical current, the word means the flow of electrical charge, the movement of electrical charge. That's what electrical current means. One of the most amazing things about electricity, which at its heart is so simple, you've got positive and negative charge, attract and repel, is that out of that emerges two classes of materials. One class of material or substance that we call conductors, another class of material substance we call insulators, and conductors have the property that the charges can flow freely through them, whereas insulators don't have that property. So it's amazing really that out of such a simple interaction with positive and negative charges and attracting and repelling, you get this emergence of two really important classes of materials for our everyday world, insulators, conductors. Anyway, the flow of charge in a conductor is what we call current. It's what we call electrical current. And I'm going to introduce electrical current on this slide from a sort of a big picture perspective, and then on later slides from a microscopic electron level or ion level perspective. Anyway, let's talk about electrical current. Imagine this cylinder here, blue cylinder here, is some conductor, some cylindrical volume of conductor. And imagine that in this conductor, the conductors, the charge carriers, are actually positive charge carriers. Now, normally we always think of metals and electrons being the charge carriers, and they're negative. But to start with, we're going to think about some sort of conductor that has positive charge carriers. It could be salt water, right? That can have positive charge carriers, so it does happen. Between the left and right ends of the conductor is applied a voltage difference, say from the battery. And I'm assuming in this sketch that over here is the more positive electrical potential. over here is the more negative electrical potential, and delta V is the potential difference between the two ends. So there's a potential hill here, and in this picture over here on the left, this is the top of the potential hill, and over here on the right, this is the bottom of the potential hill. And so if you walk from left to right, you walk down the electrical potential hill. Now for positive charge carriers, so here's a positive charge carrier, here's another one, another one, another one. For these positive charge carriers, this top of the electrical potential hill also corresponds to for them, positive charges, that's the highest point of their electrical potential energy. So they have the most electrical potential energy over here on the left, and then they fall down the hill and they have the least amount of their electrical potential energy over here on the right. And so we're watching in this picture, I wish it was a video, but it's not, it's just a picture. If we were watching it, we would see those positive charge carriers streaming like raindrops from the left to the right as they roll down the potential hill as they move from higher electrical energy to lower electrical energy. We can quantify this flow of charge from left to right by electrical current. I is the symbol that we give to electrical current, and the definition of electrical current is the amount of charge that flows past a certain location. Let's imagine this location here. The amount of charge that flows past this location or through this location per unit of time. This is our master equation. This is what defines current in terms of charge. It's just the rate of flow of the charge. That's all it is. The charge is measured in coulombs. The time interval is measured in seconds. The ratio of charge over time interval, that's coulombs per second. We shorten it to amps. And so 1 amp is one coulomb per second. So that's a picture of current flow, charge flow, and a definition of electrical current in terms of the charge's motion. I said that the picture was of positive ions moving from left to right down the potential hill. And there are salty waters that have positive ions that are the charge carriers. More common in metals, in wiring, it's electrons, negative charges, that are charge carriers. So this slide just pictures the case for negative charge carriers, notably electrons. It's the same slide in the sense that over here on the left of the cylindrical wire now is the positive terminal. So this is the higher potential. Over here on the right is the lower potential. So down the potential hill is still from left to right. However, whereas the positive charge carriers, they fall down a potential hill from higher energy to lower energy. Remember that electrons actually fall up the potential hill as they move from higher electrical energy to lower electrical energy. So these electrons that are streaming right to left rather than the positive charges that were streaming left to right, these are falling down the electrical potential hill. They're likewise moving from higher electrical potential energy to lower electrical energy. So electrons over here have high energy, electrons over here on the left have lower electrical potential energy. Conventionally, so that's a potentially confusing thing, right? You can have positive and negative charge carriers. They move in opposite directions. But if they're moving in opposite directions, they effectively move charge in the same direction, because if you move negative charge to the left, that's like moving positive charge to the right. So we define the direction of the current always to be the direction of the positive charge carriers. So electrons, negative charge carriers moving to the left corresponds to an electrical current that's going to the right, just like the positive charge current is going to the right. So if you notice on here, I still picture the current as towards the right, although the negative electrons were moving towards the left. So that's a a little subtlety or a little trap, but we have to face the fact that there are, unfortunately, well, not unfortunately because there wouldn't be life, but there are positive and negative charges. There's an analogy to the flow of an electric charge through a wire or through a fluid. And one analogy is the flow of water, a mass or volume of water over, say, a waterfall, right? This water here is moving from higher, not electrical energy, but higher gravitational energy to lower gravitational energy rather than electrical energy, just like the electrons or the positive ions were, in both cases, moving from higher electrical energy to lower electrical potential energy. So this flow is kind of down an energy hill, and we could quantify this flow as not the number of coulombs per second of charge down an electrical potential hill, but we might quantify it as the number of kilograms per second of water down the potential hill, and the number of cubic meters of water down an electrical potential hill. So if you want to visualize the electrons or the ions moving through a wire or through a fluid, then you can visualize, water falling down a waterfall. It's very similar. Okay, so that's macroscopic picture of current as motion of charge and definition of current in terms of the amount of charge you're moving. Let's talk about a more microscopic picture. In the microscopic picture, we're going to look in detail at, I'm going to pick the example of electrons flowing through a wire, but we could have picked positive ions flowing through a salty water, something like that. But I'm just going to now focus on the electrons moving through a wire. And so it's going to be a more microscopic picture where we see the individual electrons and think in detail about the individual electrons. It's also going to be a picture where we introduce a second equation. It's the equation listed on this slide, but I've got to explain it. Okay, so here's the section of wire again. Here's a potential difference across the wire, maybe confusingly. I've reversed the terminals here. So now the negative terminal is on the left and the positive terminal on the right. That means this is a lower electrical potential here on the left, higher electrical potential here on the right. So that's one change I made. The other change I made was to actually take one electron, here it is, and just picture in detail its path from the left to the right. And what's really interesting is those electrons don't just smoothly glide along from the left to the right. Positive ions don't just smoothly glide in the direction they flow. There's two motions that are superimposed. One motion, I'm sure you know about this, is that those electrons are frantically moving around due to thermal motion. They're randomly moving around due to thermal motion. So in the absence of the electrical potential on the wire, those electrons are moving around at high speed. They're just getting nowhere. So they're moving around at high speed, kind of bumping into the ions, metal ions in the lattice, but they're getting nowhere. When you switch on the potential between the ends of the wire, you still have that random motion, the electrons frantically at high speed moving around, but on top of it, you layer an additional motion that is is essentially an additional slow drift of the electrons falling up the potential hill. Remember, they go up the potential hill, or moving from higher potential energy to lower potential energy. So that's what I pictured here with this, with all these paths that I'm imagining. Here comes the electron. It is drifting towards the right-hand side, but it's also frantically bouncing around due to the thermal motion inside the metal. And so this path here is meant to be a superposition of the random motion in the material that's thermal, and you're not going to turn that off, but then this sort of constant, steady drift motion of the electron in the material that's present when you've got a potential between the ends of the material. So we're seeing the superposition of those two things. Okay. In addition to the little sketch of our electron being a superimposed, frantic, and gradual drift motion, I've added a bunch of definitions of a bunch of quantities, because these are key to this equation for the current in terms of the motion of electrons themselves. So each electron has a charge. So it's because the electron has a charge that there's an electrical current as it gradually moves from the left to the right. Each electron has a drift velocity. So this is not the thermal motion. This v underscore d is just that consistent gradual drift from left to right. So that's the drift velocity in meters per second. These are electrons. There's not one electron in a real material. There's many electrons in the real material. This is the number density of the electrons, or the charge carriers. So this little lowercase n is the number of electrons per cubic meter. And it's a huge number. It's not, I mean, million is a huge number, but this is a really huge number. When we see this number. And then here's the cross-section of the wire. So it's like the wire is like a pipe. If you thought about water flowing down a pipe, that's analogous to the electrons flowing down this pipe. The current depends on how big the pipe is, just like the current through a water pipe the current of water would depend on how big or small the pipe is. You can get much more water out of a big fire hose than you can out of a garden hose. That's because it depends on the cross-section of the pipe. We know that from common sense. Anyway, this equation here puts together all these things to write the current in terms of the motion of electrons. So this is the microscopic thing about it. It's writing that current, that just coulombs per second, or amps, in terms of actual motion of actual electrons. The current is equal to NEV VD, because drift velocity, times A. And I'm not going to derive this, but let me just argue that it sort of makes sense, right? There's only current because the electrons have charge. That's the first thing. So it's going to depend on the electron charge. There's only current if there's a drift motion from the left to right. If there's just random motion, there will be no electrical current. So it must depend on this. It must depend on how many of those electrons are drifting from left to right. If there's more in the material, copper has a lot, then you get a lot of current. If there's less in the material, aluminium has less, then you'll get a lower current. So it depends on N. And as we said, right, fire hose versus garden hose, the size of the pipe matters. So the cross-section of our wire, number of square meters cross-section of the wire, also matters too. You roll all those ingredients together. This is the microscopic picture of the current flow in terms of individual electrons drifting left to right. That's the second equation. Here's, because I stole this, there's not enough pixels, but this is meant to be an analogy to the electrons moving through a copper wire. Remember, the electrons are moving through the copper wire, but their motion is being impeded by the ions in the wire. They're bumping into the ions. That was the picture I showed. Water coming down a stream, a mountain stream. That water is impeded by the pebbles and the rocks in the stream. And so the ions in the metal are kind of dissipating the electrons' drift motion from left to right, just like the pebbles and rocks in a stream are dissipating the motion of the water down the mountain. And so these are kind of analogous. In both cases, the pebbles and rocks and the ions in the lattice, the metal, they're dissipating the energy of the electrons by the electrons of the water just bumping into the pebbles, rock, or ions. Okay, let me show you an example of the analogy to electrons moving through a wire. We said electrons moving through a wire, there's kind of this randomness to the motion, and then there's a drift component to the motion. If I drop some of these little ball bearings through the... Oh, crap. Of course, I have no idea which one of these 4 unlabeled buttons does what I want to do. I'll have to do it at the other side. Anyway, I'm just going to drop these through. I hope you can imagine, they're kind of like raindrops, don't you think? Raindrops falling. They don't just keep getting faster and faster under gravity. Obviously, they're continually experiencing the gravitational force. But rather, they kind of reach a terminal velocity because they're hitting the nails. And so the ball bearings there are the electrons moving through the wire, and the nails there are the regular lattice of positive ions in a metal. So a metal wire is a regular array of positive copper ions with this stream of electrons trying to get through it, trying to drift through it. And so that's one analogy. I can show you another analogy. So these are raindrops falling towards the ground. They're falling under gravity towards the ground, but they're not getting faster and faster. They're not getting faster and faster because the raindrops are hitting all the atoms and molecules of the air, and that's dissipating energy, just like rocks and pebbles in the stream, just like the bed of nails for the ball bearings, and just like the copper ions for the electrons in a copper wire. Okay, this is a calm video or mindfulness video. I think this one too. I kind of like it. I could spend the next hour watching it. But anyway, we must go on. I think I wanted to do an example. Yeah. Here's an example of a wire and electrical current. It's an example where we've got a 200 kilometer long wire. That's how electricity gets around, the US, is long wires, and it's carrying a electrical current. That's how electricity gets to our homes and businesses. So we're going to think about one of these. When you see these pylons, you see the wires that are stretched between the pylons. We're going to think about a 200 kilometer long wire that's stretched between pylons from one place to another place, from the power station to your home. How long would it take an electron to drift down the wire? And so we're going to figure that out. The information we're given is the length of the wire, 200 kilometers, the diameter of the wire. They're big fat wires. They're 4 centimeters in diameter, 2 centimeters in radius, and we're told that the wire is carrying 1,000 amps. They have to carry large currents because it's going to not just your home but many homes. So that's the information we're given. There's one other bit of information I looked up to solve this problem. of figuring out, because the problem is asking us to figure the time it takes an electron to go down the wire, to travel that distance. To figure out the time it takes the electron to go down the wire, travel that distance, we've got to figure out the speed that the electron travels at down the wire. Once we get the speed, because we know the length, we can use the definition of speed to find the time from the distance traveled and the time taken. So that's basically plan. So the plan is I'm going to solve that last equation for the speed of the electrons traveling down the wire, drifting down the wire, and then I'll finally find the time. That's the problem. I've said that now, and I can't remember what I was trying to say before that. I've completely forgotten it. Anybody know? No, nobody knows. I don't know. So we'll just get on with solving it. Oh, it was there's one other number beyond which we were given in the problem that I needed. The one other number that I needed was that little lowercase n. It's the number of electrons in the wire. It's the number of electrons per unit volume in the wire, in the copper wire. And I actually looked that up. And that's this guy here. So it's huge, isn't it? It's nearly 10 to the 29 electrons per cubic meter that can flow through the copper. So it's an absolutely huge number. I'm going to do this on the document camera. So I started it here by writing down all the numbers we're told. There were 4 numbers in the problem that we were told, 3 numbers in the problem we were told. I calculated the cross-sectional area of the wire, I called it uppercase A, from the radius of the wire that was 2 centimeters, or the diameter of the wire that was the 4 centimeters. So if you look on the list of numbers here, I've got the area is 12.6 square centimeters. I calculated that from the radius being 2 centimeters and pi r squared. So I did already do that. And I've also added on this list of numbers, this number that I had to look up in the textbook, which is how many electrons are there per cubic meter in copper, and it was 8.5 times 10 to the 28. I'm going to find, as I say, the speed of the electrons and then the time they take to move down the length of the wire. So to find the speed of the electrons, I'm going to use that equation that the current is, I've got to write it down and then talk about it. NEVA. Okay, those are those 4 quantities that relate the motion of the electrons that carry charge to the current that they carry along the length of the wire. And if you look at this, we know the area, we know the current. So the area was 12.6 centimeters squared, the current was 1 kiloamp. We know the electronic charge. I didn't write that down actually, but I could. And we know the number of electrons per cubic meter. That's the N here. The only thing I don't know is the velocity of the electrons, the drift velocity, and that's what I said I wanted. So this is perfect. I can rearrange this. VD equals I N E over A. I can fill in all those numbers, right? Now, again, I'm never going to be able to write out all those numbers. You have to be careful, right? 200 kilometers, you've got to fill it in meters. So it's going to be 2 times 10 to the 5 meters. 12.6 square centimeters, you've got to fill it in meters squared. So you've got to divide it by 10,000 to get a square centimeter into a square meter. The kiloamps, you've got to fill it in amps, not kiloamps. So it's going to be 1,000 amps. So you've got to be careful about all those things. But if you do this, I get a speed 5.6 times 10 to the minus 5 meter per second. Oh, When I first found that out, I kind of thought, oh, gulp. That's really slow, right? The electron's thermal motion is, I'll make it up, thousands and thousands of meters per second, really fast. The electron's drift motion is incredibly slow. Look, this is 5.6 times 10 to the minus 5. You know, doesn't even go 10 microns. The size of, I don't know what, the size of cross-section of your hair in a second. This is worse than a snail. This electron is worse than a snail as it drifts down the wire. It's incredibly slow. So that's the first thing to recognize. Electrons' drift motion, unlike their thermal motion, is very, very, very slow. Their thermal motion on everyday scales is very, very fast. So that's kind of interesting to know. If we want the time that it takes them to get down this length of wire, then let's think about the definition of speed or velocity. Is the distance traveled, which would, in our case would be the length of the wire, divided by the time taken. That's the definition of speed, right, or velocity. So I could turn that around and find out the time that it takes by dividing through by v, multiplying by t. It'd be L over v. The longer the wire, the longer it's going to take. The faster the speed, the less time it'll take. Again, if I plug in all the numbers, this really tiny velocity, this 200,000 meter distance, you get an enormously long time. It's 3.4 times 10 to the 9 seconds, enormously long time. Here's a useful number. The number of seconds in a year is pi times 10 to the 7. It's not exactly that, but there's this thing that it's stuck in my head. This is pi, roughly pi, times 10 to the 9. So this is about 100 years. So an electron, given the opportunity, would take 100 years to get down the wire from the power station to your house. And so that's also an amazing number, more like 110 years, actually. Any questions on that? Because I want to move on to resistance, resistivity, Ohm's law. So let's do that. Let's change the projectors. Okay. Sorry, I'm not reading my email. My watch has run out of power. Great. And so I'm looking at my phone to just panic myself about the time. Ohm's law. We're going to talk about Ohm's law, and then we're going to talk in a bit more detail about resistance and resistivity. So I've got a couple of slides on each of these things. Ohm's law comes from George Ohm, famous scientist, more than 100 years ago, is Ohm's law. And Ohm's law brought George must be in the room. Ohm's law brought as organization to how much current flows through a wire. So what George Ohm did was apply voltages to samples of wire and measured the currents that flow through the wire. So here's a picture basically of his experiment. Using Volta's battery, he applied potential differences to samples of wire, and then he measured the currents that flow through the wire. And what he did was change the voltages and measure what happens to the currents. And he discovered a very important fact about a lot of substances, about conductors. And that is, in general, that the current that flows is in proportion to the voltage that is applied, the potential difference that's applied. So if you apply more current, if you apply more voltage, you get more current. Obviously, if you turn the voltage off, you get no current. So that makes sense. But the higher you make the voltage, the greater the current. I actually repeated his experiment, you'd be pleased to know. Here we are. And I'll play this. So this is, let me turn the lights down. This is an arrangement, it's not a battery, it's a power supply, but think of it as a battery. It's connected to a resistor. This is a weird resistor, but it is a resistor. And with those two devices, I'm measuring the current on the left and the voltage on the right across the resistor due to the battery. I'm repeating Ohm's experiment. If only I would have been born, 200 years ago. Well, I would be dead now, so it's not a good idea. But anyway, look at the two needles. The bigger the voltage on the right, the bigger the current on the left. This is literally Ohm's law in action. The current is proportional to the voltage. And so that, at the time, was an absolutely massive breakthrough. It underlies all our understanding of electrical circuits. And so I wanted to show in real life there, Ohm's law in action. Let's stop this. So that's Ohm's law. The coefficient of proportionality between the current and the voltage is called the resistance of the material. So if current is proportional to voltage or voltage is proportional to current, then there's a coefficient of proportionality, and we call that the resistance. And the way we write it is that the voltage across the material equals the current through the material times the resistance of the material. The way we write it means that if the resistance of the material was larger, we give it the symbol R. If R is larger, then the current will be smaller for a given voltage because they're products equal to the voltage applied. If the resistance of the material is small, then the current will be larger through the material for a given voltage. So it's the product of the current and the resistance that is equal to the applied voltage. Here's a question based on that. Okay, well, we're used to thinking about wires being resistors, or say a lamp is a resistor, a light bulb is a resistor. In your phone, your laptop, there's hundreds, thousands of resistors. But our body is full of resistors too. In a cell, as you know, there are little pores from the outside to the inside of the cell, little ion channels. And those little ion channels, little pores, they're natural resistors through which current can flow. And so this is a question not about a man-made resistor, but actually about a natural resistor, an ion channel in a cell. So we're told that, so the ion channels between the inside and the outside of the cell membrane, between the two conducting fluids on the inside and outside. The ion channels are tiny, right? The membrane thickness is only 10 nanometers or something like that. The diameter is maybe 1 or 2 nanometers. So really, really tiny little wire, you could think of it as. That's what I pictured it as here, as if it was a wire. We're told that a particular ion channel has a resistance that is 50 gigaohms. A giga is 10 to the 9. So this is 5 times 10 to the 10 ohms, so it's a large number in ohms. We've got 70 volts millivolts across that that resistor. That's a resting potential of a cell. We're told that ion channel, here's my cartoon of it, is switched on and then off. It's switched on for 10 milliseconds, so a hundredth of a second, and we're going to figure out the amount of charge that flows through the ion channel in that 10 milliseconds by first figuring out the current that flows through it, during the time it's switched on with Ohm's law. So that's the basic plan here. So let's go ahead and do that. I think I'll do that on the document camera too. I've started it, of course. Here's the information we're given. This is the ion channel, now horizontally. 70 millivolts from end to end, from the inside of the cell to outside the cell. Resistance of 50 giga-ohms, 5 times 10 to the 10 ohms. It's that channel switched on for 10 milliseconds. That's quite typical in a cell. How much charge flows? We're going to figure that out by figuring out how much current flows. We'll figure that out with Ohm's law. So let's start with Ohm's law. Ohm's law, remember, is this big discovery that the current is proportional to the voltage for many materials, V equals IR. I want the current. So I've just got to turn Ohm's law around. I can turn it around because I know the voltage that is across the ion channel or resistor. It's 70 millivolts. I know the I know, what am I talking about? I know the resistance of the ion channel because we were told that. And so I just got to plug in this 70 millivolts and this 50 giga-ohms. So this is 7 times 10 to the minus 2 volts. Got to plug it in the appropriate units. This is 5 times 10 to the 10 ohms. It's obviously a tiny number over a big number. If you calculate that, I get a current, so in amps or coulombs per second, it's 1.4 times 10 to the minus 12 amps. That's the current. So it's it's a very, very small current through this little ion channel. Maybe not surprisingly, right? It's much less than electrical currents in man-made electrical circuits because it's just a tiny cell and just a little pore in a tiny cell. What is the amount of charge that flows through? Well, to find the amount of charge that flows through, let me not start there. Let's use that definition of current. Current was the amount of charge that flows divided by the time over which it flows. I wrote it before as delta Q over delta T. I'm just going to get fast and loose with dropping deltas all over the place. So this is just current over time. I know the current, I know the time, it was 10 milliseconds, so I can turn this guy around and I can find the charge, and the charge will be IT. And if I feed in this current here and feed in this time here, it's just going to be 10 milliseconds is 0.01 seconds. 0.01 seconds is, so I've got 0.01 times this 1.4 times 10 to the minus 12. It's just going to be I don't need to write it down, I can do it in my head. 1.4 times 10 to the minus 14. This is now coulombs. Not coulombs per second, because I multiplied by time. So that's the amount of charge. Remember that, here's an interesting thing. So that's the amount of charge. It just seems like, oh, that's a really small amount of charge. Wow. But think about it in terms of electronic charges. These are ions that carry electronic charges that are flowing through the ion channel. 10 to the minus 14 is about 100,000 times bigger than 10 to the minus 19, which is the size of electronic charge. So this is not much charge, but it is tens or hundreds of thousands of ions passing through that pore. Cells contain maybe tens of millions of ions on their inner and outer walls. So you need many pores to change the resting potential of a cell. So there will be, this is one pore and the charge that flows in, but there would be many, maybe 100, maybe 1,000 pores in a cell. I have no clue, you know it. Any questions on that one? That was Ohm's law. Let's move on. Gosh. Resistance and resistivity. These are two related, connected things. They obviously have sort of the same name, resistance and resistivity, but they are distinct. The resistance of the, yeah.
The slides are on.
Oh yeah, thank you. It just saved us. Doing that never stops. I can tell you that. I'll be doing it in the last lecture. It will just never stop, like a number of other habits that I have. Resistivity and resistance. Rho is resistivity. Resistance is R. Resistance is measured in ohms. Resistivity is measured in ohms meters. We'll see that. We're picturing here say a section of wire that has a certain resistance. That resistance of the wire is determined by the material of the wire, so it matters whether the wire is copper or aluminium or whatever. It also matters the length of the wire and the cross-sectional area of the wire. All those things, the geometry of the wire and the material of the wire, determine the resistance of the wire. As an example, just use your common sense here, right? The longer the wire, it's going to have more resistance, right? There's going to be more ions to hit. So we know that the resistance will be proportional to the length of the wire. Cross-section of the wire, just remember the garden hose and the fire hose. Obviously, the bigger the cross-section, the fire hose, the lower the resistance, more current can get through. So the resistance is going to be inversely proportional to the area. So the geometry dependence, we just use common sense, right? It's got to depend on the length of the wire, proportional to L. It's got to depend inversely on the cross-section of the wire. So it's going to depend on L over A. The remaining quantity in determining the resistance of the wire is a quantity that's called the resistivity. It's a characteristic of the wire's material. So this is the quantity that depends on whether you've got copper wire, aluminium wire, some other type of wire, or whether you've got extracellular fluids in a ion channel. So each of those has a resistivity that characterizes the material, and that's what we call rho. So put that all together and you get the equation that's on this slide at the bottom of the slide. The resistance of the wire as a whole is equal to the resistivity, so that's the material it's made from, and there's tables of resistivity, times the length, the longer the wire, the greater the resistance, divided by the area. The greater the area, like the fire hose compared to the garden hose, the smaller the resistance. So this is how we understand the geometrical and material dependence of resistance of a wire in terms of resistivity and geometry. Here's a question based on that, a quiz question. So let me go and publish this. Here we are. In this question, we got 3 sections of wire. They're all identical materials, right? The resistivities of A, B, and C are all exactly the same. So don't worry about the resistivities. Just worry about the geometry. You've got to figure out, based on the geometry, which one has the largest resistance, which one has the smallest resistance, and which one has the intermediate resistance based on the geometries of these 3 wires. You can see that they have different lengths and they have different diameters, different areas. So I'll give you a minute or two to think about it. Okay, let me give you the answer and we can check we all got it right. The material that has the largest resistance is that material is, which actually I've got to read it, rank from largest to smallest. So we want the largest resistance. Who has the largest resistance? Resistance goes up with length, and resistance goes up as the cross-sectional area goes down. Wire B is the longest, and simultaneously has the smallest cross-section. So it combines the longest wire with the smallest cross-section wire. Both those make the resistance larger, and so wire B, or item B, has the greatest resistance. The one with the smallest resistance, for small resistance you want short length and you want a fire hose, you want large cross-section. C has the shortest length and it has a large cross-section. So if you were to rank them in order of resistance from largest to smallest, then B has the largest resistance, C has the smallest resistances, and A is in between B and C. Is everybody okay with that? Okay, that's good. Just wanted to show you one more demonstration of this time of resistance and resistivity. And resistance's dependence on geometry. As I was saying, just to drill it home, that the resistance of a wire depends on the length of the wire in proportion to the length of the wire, and it depends on the cross-section of the wire. It decreases as the cross-section grows. So in this, let me start this video. We've got various wires here. This bottom one here is a silver wire, no expense spared, and its diameter is 1/4 millimeter, and I'm going to measure the resistance over this length of it. It's 1.3 ohms. So that's the resistance of this length of this diameter of wire. I'm then going to roughly halve the distance, halve the length. So now I'm going to be measuring the resistance of the wire over this length here, and if we go upstairs here, it's about half the resistance, right? It was 1.3 ohms and now it's 0.7 ohms. So that's about half the resistance. So this is the fact that the short wire, length of this wire, had a low resistance. The long length of the wire had a proportionally large resistance. Now I'm going to go up to the wire above. Okay, this is a thicker wire, the same material. What's the resistance for this this short length here? Well, it was for the small diameter wire 0.7 ohms. Now it's about 0.3 or 0.4 ohms. So this fatter fire hose wire compared to this garden hose wire has indeed a smaller resistance. And then finally, I think I'm going to look at the resistance by doubling the length of this wire. If I double the length of this wire, I get roughly double the resistance of the wire. And so it depends on the length. In the experiment that I did, I was a bit sloppy when I was doing it. I was in a rush, and I wasn't overly careful, so it wasn't always exactly double the length and so forth. I'm not sure it's exactly the right proportions of wire, but that basically reflects the dependence on the length of the wire and the cross-section of the wire. Okay. Last topic for today. Energy and power. Because we said that circuits involve electrical energy, they involve electrical power. Here's just that, recycling that picture of the charges flowing through a circuit, say along a length of wire, or through an ion channel, whatever you like to think. but I'm repurposing it in the context of energy and power to introduce two new equations. This is an equation-rich, you'll be pleased to know, slide. There's an equation here about electrical energy. That's the one on the left. Equation over here about electrical power. Remember, that's the rate of transforming energy. So this equation here is the equation for the electrical energy that's dissipated, so that's the delta PE, when charge is moved through a potential difference of delta V. So in this picture, I'm moving charge Q down a potential hill, delta V, that releases electrical energy, and this is the amount of the change in electrical energy in terms of the charge that I moved. And so that's an important equation. Really, it's an equation from a few classes ago when we first met electrical potential. Because we defined the electrical potential in terms of electrical energy. We define the change in electrical potential in terms of change in electrical energy when a charge is moved from one place to another. And that equation from the earlier class is exactly this one here. It's the relationship between potential and energy, but now we're thinking of it in the context of a circuit. Whenever you see charges move from one potential to another potential in a circuit, they're releasing electrical energy. And so we can keep track of, with this little master equation for potential and energy, we can keep track of the energy that is released in the electrical circuit, dissipated in the electrical circuit. We can also keep track of the rate at which it is dissipated. So power is just energy divided by time. Energy is joules, power is joules per second, or watts. It's the rate at which we're dissipating, releasing energy. So all I'm doing is dividing the energy in this equation on the left by time interval to get power from energy, is given the symbol P, as you've met in 211. If I divide the equation here on the right by time, the charge becomes current. That was our definition of current in terms of time. And so this is an equation for the power being released in a circuit, the joules per second in a circuit, in terms of the current that's flowing and the potential difference through which that current passes. And so that's another very handy equation for keeping track of power dissipation, energy dissipation in a circuit. Look, both of these equations then weren't really new equations. I just drew on prior knowledge about the relationship between energy and power and prior equations that we've met for the definition of current, for the definition of electrical potential, to write down these equations. So they're built on previous equations, but they're very, very useful in analyzing electrical circuits from an electrical energy perspective. That's the value of them. And I think, therefore, I've got a problem that I wanted to work out. And I'll try and get through A and B. Maybe we'll just get through A. I don't know about that. In this example, I got a very basic electrical circuit. That is electrical circuit with a battery and a resistor. So a flashlight is a very simple circuit that has a battery, obviously, and it has a lamp that is a resistor. And it's just exactly that circuit with a switch that I first mentioned at the beginning of the class, the circuit that we're analyzing today. So now let's take a look at it from the perspective of energy and power. So we're told in this problem that I got a flashlight. It has a 1.5 volt battery in it. A current is flowing in it of 0.1 amps, and it flows for 12 hours. I'm going to figure out a couple of things in part A. What is the energy and power delivered by the battery to the lamp? dissipated in the lamp. We're going to figure out the energy and power perspective on this electrical circuit. If I got time, I'll figure out how much charge flowed and how many electrons flowed. But if not, we can just look it up. I think I was going to do this on the document camera. And I started it. Here's the circuit. So here's the battery, 1.5 volts. Here's the here's a resistor, which is the lamp. I don't know the resistance actually, but I do know the current that's flowing. We were told that's 0.1 amps, and I do know that, like I always do with all my tools, I either leave them out in the kitchen, or I leave things switched on, like the flashlight. I left it switched on overnight for 12 hours. And so we're gonna figure out what was the power being consumed by the flashlight and what was the energy, the total energy that was dissipated by the flashlight being on for 12 hours. The power is easy based on our last slide. Remember that the power dissipated is the product of the current flowing in the circuit times the voltage difference. So the power being dissipated by the light bulb in the flashlight is 0.1 amps, that's the current that flows through it, times 5 volts, that's the voltage across it. So this is 0.1 amps times 1.5 volts, that's equal to 0.15 watts or joules per second. So that's the current. That's the power being dissipated. Now I can calculate the potential energy that was dissipated for the 12 hours. Remember that power is energy divided by time. That's the definition of power. Is the amount of energy dissipated in a given amount of time. And so energy is equal to power times time. That's just rearranging the definition of power. I know the power, 0.15 watts. I know the I know the length of time it was on. It was on for 12 hours. I've got to put that in seconds though. I've got to put it in SI units. So you've got to multiply 12 by 3,600. That's the number of seconds in an hour. And that came out to be 43,000 seconds, roughly. And if we multiply those, that's 6,480 joules. So that's the energy dissipated. So rather wastefully, I wasted more than 6 kilojoules by leaving the flashlight on. That's a large amount of energy, and that was stored in the battery. That's a remarkable thing about batteries. I think I really have run out of time. I just want to point out that the second part of the problem, which is how much charge was moved around the circuit, how many electrons was moved around the circuit, is in the slide. And so the second part of the problem I worked out downstairs here. You might want to look at that. We covered electrical current, 2 equations for it. We covered Ohm's law, resistance and resistivity, 2 equations there.